This video is about large turbine modelling improvements that we've added in Bladed 4.16. We have three presenters today. That's myself and two of our engineering developers, Sigurd and Galih. We're going to talk about three large turbine modelling topics: the IEA 22 megawatt reference turbine, and Sigurd's going to talk about blade 6x6 structural modelling, and Galih's going to wrap up with talking about wind farm generation upgrades, and then we'll have a quick what's next for large turbine modelling in Bladed. The first topic we're going to discuss is the IEA 22 megawatt reference turbine. So this 22 megawatt turbine has been designed as part of IEA Task 55, and that work was led by NREL and DTU, and we've been supporting them in this work, building the model in Bladed and also running a code comparison study. So why are we interested in reference turbines? They have many uses. For example, might be able to do substructure concept design based on the loads from the large future turbines. And we can also do studies researching how well the model assumptions that we've made for decades of wind turbines, how well they work for very large turbines that may be deployed in the future. So I'm going to start by doing a demo, having a look at this model in Bladed. So you can see here I've got Bladed 4.16 open, and I'm looking in the installation directory at the demo models IEA 22 folder. And you can see inside that folder, first thing to look at is the Bladed project file. So I've got that open. I'll have a quick look around the model. So here's the turbine model. You can see we've got about 180 meter height and 280 meter diameter. So we'll have a look at the blade. Here you can see we've got all the blade stations defined. The blade length is 138, 7 meters pre-bend at the tip. You can see all the section data, the aerodynamic geometry, and the structural data is all there to be examined. Also worth a look at the controller screen. We've got the Roscoe controller, so there's a power production controller that comes with this turbine, so you can run time domain simulations. The next thing to look at is the verification report. So we've got this PDF. We'll have a look inside there. So this is the report, and there's a few main sections: the turbine description, the model definition of all the subsystems and how we've defined them, and then the model verification. So we'll just dive in quickly to one of the subsystems, and you can see the wind IO parameters there. This is the source data that was defined for the turbine, and you can see the corresponding Bladed parameter where we've translated it to Bladed for all the different sections. And further down here, there's frequencies of the tower modes, and then also some steady state operational plots, so we can see that the turbine is behaving as expected. So finally, just to note, the wind IO to Bladed converter is also here in this folder, which provides a Python tool to convert wind IO blade data to Bladed. And Sigurd's going to say more about that in just a minute. So final thing to just say about this topic is that we've done a code comparison study that's been presented at the Talk 2024 conference. So we've run simulations in 4 aeroelastic codes: Bladed, Hawk 2, OpenFast, and QBlade, in collaboration with DTU, NREL, and TU Berlin. And we've run different load cases in these tools, such as steady state analysis, where we look at the operational conditions, loads, and deflections that you get with varying wind speed in the steady state. We've looked at azimuthal variation cases, where we look at how the loads and things like angle of attack vary with the rotor azimuth. And we've got linear stability analysis, where we're looking at the frequency and damping of the turbine coupled modes, and also time domain simulations. So the general conclusion of this is that these 4 tools are giving consistent steady state results for this IEA 22 megawatt reference turbine. The dynamic cases identify areas for further study to mitigate risk with ultra large turbines. So we can see differences in the dynamic cases between the codes, and that gives us areas for further investigation to understand why those differences occur. And you can go and find the full details of this in the Talk conference proceedings. So I'm going to hand over to Sigurd now to talk about blade 6x6 structural properties.
Yeah, so I'm going to talk a bit about today about the blade 6x6 structural properties. So in relation to the bladed model we have today, and also about some of the work that we've been doing using a wind IO to bladed converter tool that we have made. So to convert from 6x6 matrices at a reference axis to a bladed compatible format. And then finally, I'm also going to touch upon briefly a verification study that we've been doing using BKAS, which is a cross-sectional analysis tool. So just to dive into it, so the whole sort of essence of blade modeling in our sort of case is that we want to go from a three-dimensional solid blade with sort of continuously defined structures and materials to a finite beam element model. So the procedure is sort of to take this full model and define a mesh and material associated with this mesh, and then sort of decide on a finite set of 2D cross sections that you want to extract your beam node information at. So each of these cross sections can then, for example, be input into a cross-sectional analysis tool such as VEPS or BKAS to extract the structural properties for the beam elements, which then in turn gives this beam element that is suitable for bladed. So this means that each section has a unique 6x6 stiffness and mass matrix for each location and orientation. So what do we mean when we say 6x6 cross-sectional matrix? Shown here on the right is a 6x6 matrix that relates the strains to the forces and moments. So it's relating those two, and in this case, the 6x6 matrix is associated with a reference axis, and it can also take other shapes if it has more complex material models, such as a fully populated anisotropic model, and it can also be simpler if it's if model assumptions are made. So this is sort of the constitutive relation of a Timoshenko beam model, where x is along the beam. And what we're seeing is that this is emerging as an industry standard using 6x6 matrices. It has some really nice advantages, such as it is a really clear convention. So it's a lot of information packed in a single place, and this information is associated with a specific coordinate system, so a certain location and orientation. So it's also easy to sort of, or it's more easy to convert, like go from one model to another with this information, and also transferring it back and forth. Yeah, and it also is just much easier to see what model assumptions and simplifications have been made for this type of structure. And a big advantage as well is that it supports existing workflows using cross-sectional analysis tools. So these tools still often output these 6x6 matrices, which is then sort of ideally ready to be used in the beam finite element model. Yeah. So in bladed, we don't have a 6x6 matrix as a possible input for the user, but we do have like a matrix internally, and this is associated with the neutral axis orientation and location, which is also commonly referred to as the principal elastic axis or the bending axis. So it's shown here on the bottom right-hand side, the terms that we are capable of modeling at this point. So the green terms, they are the terms that arise from the offset between the shear sensor and elastic sensor, so where the neutral axis passes. And the blue terms are the bending twist and bending coupling terms that the user can define in project info. So now, sort of how do we connect all of this to the bladed inputs, because they are sort of slightly different. So here, the Wind.io to bladed converter tool becomes interesting. So just to give you some perspective, this converter tool sort of the inspiration for it started with the requirement to create the IEA 22 megawatt reference turbine model that Will has been speaking about in bladed. And here the information is provided in 6x6 format for the stiffness matrix and the mass matrix. So here on the right hand side you can see the open source YAML file. So it's an input file containing all the information associated with the reference turbine. And this information was defined in these 6x6 matrices that we're not capable of modeling in bladed. So we needed to convert those into a bladed compatible format. So in comes the converter tool. So this is a Python implementation as an example for the IEA 22 megawatt model, and it takes this YAML file as an input, does schema validation of it, and then converts the information into a bladed project file that can then be open. So I'll just do some demonstrations on that. So just using visual code, we can have a look at the input file. So this is the open source Wind.io model that is available on GitHub for the reference turbine. And here we can see all the different stations for the inertia matrix and stiffness matrix. And a schema that we have that sort of ensures that all the required information is there. And then it's actually just a matter of just running it as a command line tool and pointing at the input file. And then it does the conversion. So if we then look at the outputs, we can see that there is a project file output, and then we can try to open it. So this is only converting the blade, but we can inspect that. We can see now that the blade is fully defined with twist and all the mass and stiffness properties as well. So that is sort of that. And then to go along with this is actually also a theory document that describes this implementation. So if we go into the bladed online docs, that's also available on the workflow pre-processing. Then there is the description of how to go from these 6x6 matrices at a reference axis to bladed format. So the converter tool is actually located in the installer under demo models and under the IEA 22 megawatt model. Yeah, and this is sort of the simplified matrix that we are converting. And then what is interesting is this defining bladed input parameters section, where you can see how the specific bladed input parameters are actually defined from this YAML file of the IEA 22 megawatt. Then finally, if we go into the verification study, we can see the verification study we've been doing in this area using BKS. So we started sort of with having BKS output at a reference axis, then input that using the converter tool into a bladed model, and then output from bladed, and then we compare that to the BKS output at the neutral axis. And what we are, so this is showing the output of how to output the 6x6 matrices from bladed, which is then in turn provided in the $VE file. So then if we compare, we can see the bending stiffness is identical. There is a slight difference in the torsion shear stiffness term, so the coupling term K42 and K43, and also in the torsional stiffness. So those are the only three terms that vary slightly. And we did sort of an investigation into this, and we can see that it's only due to bladed sort of incapability of modeling the shear axis orientation. So it doesn't capture the shear coupling term, but in this model case, it was not that significant, the effect from it. But it's quite an interesting study to read if you're interested. So I think that was it from me. So thanks for listening, and Over to you, Galih.
Yeah, and now I would like to talk about wind turbulent generation upgrades in bladed, as we know that turbulence serve as a very important part in time domain calculations in any wind turbine simulations. And therefore, here we made some upgrades to answer some challenges that we have for large wind turbines. So here we go. So first of all, we know that the size of the wind turbine increases significantly nowadays, and therefore, what actually the requirements with the increase of the wind turbine size with respect to the turbulent inflow and how the wind file size has to be accommodating for the increase of the wind turbine itself. So we know that already that the wind turbine size increases, and this is the second part is very important, that actually to ensure that the small scale turbulent eddies are captured. Therefore, the grid size of the turbulent inflow file has to be remain small. Typically, this is below 6 meter, so it can be even smaller than that. So what is the main implications to keep the turbulent eddies to be captured, even for the small part? That means keeping the size of the grid to be constant. That means that puts burden on the computer memory because more grid points needs to be simulated when the wind turbine size increases, and therefore the wind file size also increases. For example, in the past, when we are talking about small wind turbine, probably of about 100 meter of diameter, or probably about 50 meter of diameter, then you probably just need a wind file size in the amount of probably a bit larger than that. However, when the wind turbine size increases, for example, to 200 meter of diameter, then the wind file size can increase up to, for example, 300 meter in size in both directions, for example, in vertical and also lateral dimensions. And therefore, the number of grid points can increase quite significantly in that sense. And how Bladed actually considers these challenges? That's one of the main important question that we would like to try to answer in the following presentation. So first of all, it's quite simple. Wind eddy module is actually a module that is used to generate turbulent inflow file in Bladed. It is now updated to use the 64-bit technology. And what is actually the direct implications of the updating to 64-bit technology on the turbulent wind generation? So first of all, now Bladed is able to generate turbulent wind file with a grid amount larger than 50 multiplied by 50 grid points in lateral and vertical dimensions. So it means you can generate turbulent wind file with by keeping the resolution of the grid to be small, which is good because you can still capture the small-scale turbulent eddies. And with respect especially to a MAN turbulence model, now you can assign higher number of FFT points when generating turbulent flow when using MAN model. And what is the implication when you are using higher FFT points in MAN model? The first is the quality of the MAN model that is generated is actually improved. As you can see from the following figures, so the top figure is the figure of the spectra, and the bottom figure is the figure representing the coherence of the generated turbulence when using MAN model. And the black curve will be the theoretical spectra that should be generated by the MAN model. And the picture or the lines with colors, they are generated from Bladed turbulent flow generators with different values of the FFT points. So you can see here with increasing number of FFT points from 32 to 64 and to 128, you can see here that the accuracy of the turbulent flow generated by the MAN model is actually improved. You can see from the violet to the blue and also to the red, the spectra much better with the theoretical spectra. But also for the coherence for the neighboring grid point, you can see here when you are using quite high number of FFT points, the coherence match really, really well with the coherence that should be generated by the man model at the neighboring grid point, as you can see here. And enough with the wind files and enough with the turbulence. And I think this is what is most interesting for you if you are using engineering tools such as Bladed to simulate wind turbine performance. This is one of the things is the loads. What is the implications on the loads when you are using a better turbulent inflow file, such as when you are using the man model with different number of grid points, with different number of FFT points. So this picture shows a direct implication of the number of FFT points on the man model, on the loads, especially for the fatigue load, representing the DLC 1.2. And this picture shows the plate root torsional moment. And the calculations were done on 10 different wind seats, and these were done at the ultra large wind turbine of IE 22 megawatt wind turbine. So it's quite up to date wind turbine, and the size is quite large to represent the future challenge of ultra large wind turbine size. And you can see here clearly that the plate root torsional moment is actually quite affected by the number of FFT points. And as you can see, because when we assign a higher number of FFT points, we can actually improve the prediction accuracy of the turbulent flow that should be used in plated time domain calculation. You can see here that the loads are actually affected. And this means by enabling a better prediction or better generation of the turbulent wind, this means you also improve the prediction accuracy of the loads. And what is the implication? This means that it's actually this thing is actually helpful to reduce the uncertainty and also quite helpful to mitigate risk. Thank you, and I think that's all from my side. And yeah, if you have any questions, we can discuss that a bit later. Thank you.
Thanks, Galih. Final section is what's up next for turbine modeling and Bladed. So right now in the team, we're working on Campbell diagram and linearization improvements. So you can see in the figure on the right, a preview of our Campbell diagram mode shape animator that we'll release soon. We're also working on algorithm upgrades for the Campbell diagram to for example, include dynamic aerodynamic states in a more robust fashion. After that, we'll be looking at vortex line aerodynamics and getting that released as part of Bladed. And a bit further down the road within Bladed Next Gen, we'll be adding full support for 6x6 blade matrix input to Bladed. So thanks for watching. If you want to get further information about Bladed, you can contact us on renewables support@dmv.com. You can also follow us on LinkedIn at DMV Digital Solutions.